Thanks everybody for coming today. We've got Theodor Thornhill today. Before standing here, our next speaker was actually a professional classical violinist. So everyone please welcome Theodor Thornhill and trivially bug-free code for a greener planet.
Thank you. So, as mentioned, my name is Theodor, or Theodor. I'm from Norway, Bergen specifically. I work in the largest commercial broadcaster in Norway. So we work with sports, making productions for sports like football and hockey and handball and all of those things. And we do news, and we also have we're a Netflix competitor, so we have a streaming service as well. So I'm a product architect, which means that I'm not really sure what it means, because it's a quite new position, but it gives me the opportunity to do quite a lot of research and development at my job, which is kind of nice. What we're running is a distributed system, microservices, pretty normal, standard craziness, and we've kind of inherited it from before I started, and it had a lot of issues when I first came. So what we'll be talking about today is a lot of war stories and issues and yeah, terrible problems. And mostly my slides will just be code, just a slide full of code. So and it's supposed to be here just for reference and just for so that you get somewhere to put your eyes, to rest your eyes, apart from me. So there's a prelude here, a small setup for a motivation for why I'm here. And this is a football season start. Purposely I call it football because that's the correct term. It's not, you walking with an egg in your hand thing. So 2 years ago, there was around February, there was about a month until the season was starting. And we own the rights to Norwegian football seasons, the football, everything football related in Norway. And this is quite a big deal. There's a lot of money involved and a lot of infrastructure, and we do the whole production thing, so with cameras and it's people interviewed, and it's a lot of prestige really in TU2 doing this. And around a month before it was supposed to start, we saw a lag starting to spike in our systems. Specifically, we use Kafka to stream data around. And we saw the lag was increasing at a very uncomfortable rate. And pretty quickly, we had over 500 million messages in queue, which had to be processed unless we would get a corrupted state. But we didn't really process it. It went super slow. So at this point, about a month before the season was supposed to start, we had an expected 33 days latency, which is, that's fun. That's a good way to work, So now we just had to figure out what's going on, because we have no idea. There was no reason why this suddenly didn't work, apparently. So we had to start digging. And so the part one here is a bit of a problem description and a bit of setup to what we were running. So this is a bean, Spring Boot bean. Specifically, it's what this is doing is, let's consider a football game. You have two teams, right? For example, Arsenal versus Liverpool. And what this thing is doing is that it checks the latest state that we have in our system, and it aggregates them into a list of two teams, and ships out that list of two teams. So it's pretty simple. It's just collect these two teams, they're related to this match, put it in a list, and ship it. And this is, in some sense, the most beautiful and horrible code I've ever seen. And today we're going to play Spot the Bug. And I hope that you will participate, because I brought some Norwegian chocolate. And this is what Kit Kat should have been, by the way. So, first question is, can anybody here spot the bug, or the issue, or the fault here? I'll give you a couple of seconds to think. This one is really hard. Yeah?
Will it block on initial event precedence?
No, it will not, but it's a good suggestion. So chocolate for you. Coming up. And no, I'll just throw it to you. There you go. Perfect. Yeah, so that's not correct, but it's a good suggestion. What's happening here is that this is a simple aggregator map reduce thing, where we do the initial event participants with just creating an empty list, and then we add an entry if it's the one we're going to add, and we subtract if we're supposed to update, if there's a change on the one that we already have. And this reminds me of a movie I saw long time ago, a terrible movie that was released around the same time as the first American Pie movies. It was called Evolution. And there's a scene where there's this little cute frog monster thing, and suddenly it just gulps up the whole one of the main characters. And it turns into this strange Head and Shoulders commercial, and everything is really weird. And that's how debugging this felt. Because when we subtract, this is the subtractor that's referenced in the previous part. So let's say Liverpool scored a goal, and we now want to update the state. So now it's 1-0. What we're going to do now is search through the list and find the thing, the entry. And in this case, it would be a list of 2, so it's pretty quick. So in the list of 2, we find Liverpool, and we update it with a new thing. And how we're doing it is just we're first just deleting it and running the adder and inserting it. So it's a pretty simple thing. And this looks like some code that would be recommended as, how you're supposed to write modern Java. But this is the worst code I've ever encountered, maybe surprisingly. So what's happening here is that every time we are updating anything, we need to create 2 lists, which shouldn't be an issue. But since this is Spring Boot and this is abstracted all the way, this runs on an abstraction above a Kafka topic, which means that all of these processing steps will get persisted, and they will be distributed across regions. So now you're not really updating a list, you're actually sending a list through the network, persisting it in 3 regions if you're supposed to be professional about it. Which is, now it's starting to add up. So now this is hiding a lot of network I/O, even though it's invisible to the programmer. And this is for a football game where we have two entries. Consider Tour de France, where we have an event or with around 200 participants. In our system, we could argue whether or not it's a good idea or not. This event participant, in the context of a cyclist, has all the history that we know about this cyclist. Oh, yes, I think it'll work. It's got all the history. So what that means is that every list here, every JSON that this would try to serialize and ship over the network would be around 40 megabytes, which is a lot, at least considering that now we're doing this every second for hours during a race. And it would actually amount to, when we add up everything and consider in replicating and all of that, we are suddenly trying to send over the network 460 gigabytes of data every second, which is, to me, shocking when you look at this code. And this code, well, this pod running this bean runs at around 2.5 CPU idling and between 5 and 10 gigabytes of memory, which could be a lot, it could not be a lot, who knows? But this is a refactoring I did. I'll give you a couple of seconds just to look at it. But the idea here is we don't want to allocate all these lists because this is insane. It would create so much garbage that it's absolutely untractable to do this. And remember, now we have around 25 days until his season is starting, and we're still around 30 days of lag. So we need to be able to land something that will actually manage to process this data. So what this is doing, it's the same subtractor, but it's doing a nifty little trick. It's not a super complicated thing, but it traverses the list from behind, and it finds the entry in question, swaps it with the one at the end, and pops it off. So now we have a constant time removal of the thing, rather than an allocation of 2 lists and whatever. And this, kind of simple, but it's a meteor code now. This is something that you probably, if, let's say a junior would write this, you would probably reject it, right? You would say, no, do it using the Stream API or whatever, because that's better, it's easier maintainable, and yada yada. But this is, to me, it's a lot better code. Much better. The actual code running in production has a comment just explaining it to be nice. I removed it just for brevity. And this actually reduced the memory footprint by 3 gigabytes. This changed by itself, which that's amazing in my eyes. But still, this is not enough, not at all. So, part 2. We're now starting to realize that we have to rewrite things because it's not working. We don't understand our bugs. We don't understand why it's acting as it is. Kafka Streams in Spring Boot, sorry, I'm just going to get some water. It actually has 3 different ways to persist during processing. The first thing it does is that it persists the output topic, as it should be. It also uses internal topics to keep track of intermediate states. And it also uses RocksDB as a caching mechanism to be able to, for example, have a faster boot up time. All of this boils down in the end to a double write semantic issue where if you're not super confident in what you're doing and have really PhD in Spring Boot Kafka, you'll suddenly end up in a state where RocksDB, for example, is out of sync with the internal topics persisted and distributed. And if you're really unlucky, you don't even have the same partitioning scheme on your internal topics and your output topics. So now suddenly your app just starts sleeping, it falls asleep. Because, it doesn't recognize updates. So we could have, for example, a join between 2 different topics where if updates come to one of the topics, it'll flow through fine. And if it comes on the other thing, nothing would happen. It would just be silent. And then if we force an update on the other topic and it flows through, suddenly this thing wakes again because now it's in RocksDB. And this is a huge problem that we get in many places. Let's say you want to persist something in a database and you also want to ship it on Kafka, and Kafka fails. You've stored that thing, your thing was a success in the database, and now you're screwed because you have a split brain situation. And that's really kind of CS 101 kind of problem, but it happens a lot. Surprisingly often we see this. So what I did, I wrote a library myself. It's called Go Listen, and it uses Postgres and it's a listen notify protocol. And it's a super simple thing. It just asks, well, it subscribes to a channel in Postgres, and Postgres, when something happens, you have a trigger shipping out a notification. And we then have user space handlers just to do something with the update. So now we just avoid the whole double write thing completely, which is the lifesaver. Because a lot of what we do is to receive sports data from somewhere, either from a different broadcaster or a sports betting data provider or whatever, and we massage it and we ship it internally into our company. So now every one of these connectors to the outside of our company, they only need to worry about persisting the data to Postgres. That's the only thing they have to do, which is now super simple. So now it's just, it's a get, or it gets something pushed to you, and you just persist. Database save, done. Which now, the apps that we rewrote from the previous kind of implementation to this runs now on 0.1 CPUs to around 1, and 50 megabytes of memory to around 500 megabytes, depending on the workload, which is, it's a factor of 10. So that's a huge improvement, which would then again mean that we don't have to burn down the forests as much anymore, because, for no apparent reason at all. Why should we ship 460 gigabytes of data that's mostly the same? Yeah, question?
So I just want to double check I understand what you did. So with that listener, did you just basically remove the need for Kafka all completely, or were you using that listener to push the message to Kafka?
We wouldn't remove Kafka. We would remove the need to do most of these transforms using this framework that we previously used. So Kafka is still an important thing. Kafka is our communication layer inside of Team 2. So what this does is that an application itself doesn't need to worry about Kafka. This thing is pre-configured and it's configured correctly, so it's easy to do the things right and correct if you maybe don't have a lot of experience writing distributed services. And it'll just do it for you. So you'll get a message, and you just write a simple transform function or whatever thing you want to do with the data, and you ship it to Kafka. So that's the thing it does.
Thank you.
Chocolate for you.
All right.
Yeah. I'll maybe not throw it. It's a bit far. You can either come get it now or later. Your choice. Yeah, get it. Okay, let's go. There you go. Oh, close. So there's one thing here, though. The double for loop here. This is a simple and quite naive way to just handle redeploys and downtime or whatever. So consider your application is redeploying and something happens when the thing is shut down. We need to still be able to pick up those changes. So this is just a simple way for us to hook back in. You could say something like ship everything that's happened for the last 10 minutes or 5 seconds or all of it, depending on the size. And this is actually, it's a remarkably decent way to handle it. It's simple and it's understandable. However, as we're all lazy all the time as developers, I noticed that we don't implement this, which then would leave us open to missing updates when we shouldn't miss them, just out of laziness. So even this is a good step in getting a bit further on the way to writing error-free code and code that we actually understand. We still have some foot guns here that we need to address. So part 3, enter Zig. I'm pretty good at writing code, but I'm terrible at naming, so apologies. This thing is called Kafka Pooper, and what it does is that it just consumes something from Kafka and it poops out something to Kafka. That's what you get when you're working with me. But this is a remarkably simple and decent way to handle what we're doing. Because we rely on some simple facts here. We know that Kafka has some guarantees. We could do either exactly one semantics or at least once or whatever. And we know that things will be persisted and they will be distributed and replicated. So the underlying infrastructure here is pretty well tested and well founded, which is good to rely on. And we use Avro as our serialization layer. We wrote that library ourselves, so it's zero copy. So it moves, it doesn't allocate anything. So if you get some bytes coming in, it'll be the same bytes that we ship out. What this does is that it just creates a struct that has a consume function on it, and it takes a mapper. And this mapper is just a function that comp time, there you go, comp time has an in type and it has an out type. So yeah, transform a thing from one thing to another thing. And what it does is it makes things really simple for our developers. At this part, if we got something from Kafka, if there was an update, and it had a payload, so it wasn't a tombstone, we then just open an arena, and we read the thing, and we run the mapper with the allocator, the arena, which then transforms the thing, and it just produces it out. So it's just a super simple runtime that goes. One of these mappers could look something like this. You just implement a struct, which has the pooper inside. And yeah, it just creates a key value thing. It's super simple. It's actually this simple. Any questions to the infrastructure thing here? No? Great. This is now reduced, yeah. Consider the first application. This actually does exactly the same thing, but now with 10,000 of a CPU to thousands of a CPU or something, and uses less than 10 megabytes usually. So now we're in a way different league here. And now remember, we had 33 days latency when we first started this. What would be a good latency now, considering the improvements we did? Come on. 3 days. Yeah, that would be really good. Yeah, factor of 10. It's better, though.
No latency.
Yeah, well, the latency is now around 4 to 15 milliseconds, end to end. So that's quite an improvement, I would argue. And this is a slide showing the cloud costs for running our team's infrastructure and applications. When we started, it started out at more than this, but we don't have data going all that way back. But our full fleet, from the start of the previous graph here, we ran at about 780 CPUs, 500 gigabytes of RAM, and it cost us about $400,000 a year. And now, you can see, it's a different story. The reason it's still so high on the memory and the cost, even though it's it's a 80% reduction, is because we still have some of these Java apps running. We're not completely done rewriting everything. But my goal now is that, and I mean this 100% seriously, that we should be able to run our whole staging environment on a Raspberry Pi 3, not 5, because that's way too strong. And I think we should really consider what we're doing here, because I'm worried about the future, and the reason I'm worried about the future isn't because of megacorps doing this and that and the AI and whatever. It's actually that we as developers don't really appreciate the fact that we are responsible for creating this garbage code that we do every day. And it's burning down the planet and destroying the world for our kids doing this. And it's so tangible. When you start doing this, when you start to actually fix this and don't do that anymore, things start working. You don't have any of these bugs anymore. You understand your own code. Yeah, you kind of had to write a few libraries yourself, and you kind of had to do this and that. You had to be a little bit smart about it. But that's what we're here for, isn't it? We're not here to just poop out Spring Boot code and hope for the best and debug things for years on end trying. And I mean this. I think this is a really serious message that we should be more responsible for the work that we're putting out. I think it's a huge problem, at least considering now the AI age, where it's like, yeah, we can just ship even more things and do it faster. Maybe we shouldn't. Maybe we should do it better than we did before. So thanks. That's it. So yeah, reach out to me if you want. Feel free to ask some questions now. Yeah?
So So of course, I love the message, but I got here a little bit late. Can you explain to me maybe why, what do you think is the thing that didn't cause you guys to implement this quote-unquote bug-free to begin with?
I think that's the usual thing. We try to deliver features. You have some managers who have some good intentions, just wishing that we should provide some feature first to market kind of thing, and all of us run our work environments like this, proof of concepts, MVP kind of iteration style. But we never iterate. We just create a lot of proof of concepts and let it stay, let it live in production.
So does that mean that because of the business pressures, the only way to do this is to write it really, really bad first, cost the business a ton of money, and then fix it?
It could be. It could be. That's what we did. I'm not saying that's a good idea. And I'm also saying that if I asked if I could do this before I did it, I would probably get a no. So I didn't ask. So I just did it and fixed it and said, okay, now we saved you $1 million. And yeah. But I think this is a really big problem with all of the agile methodology things and everything. Chocolate for you. Any more questions? Yeah.
So I think we're actually out of time for questions.
We're out of time. Okay, so chocolate, careful. Oh, nice.
If anybody does have any other questions for Theodor, out in the hallway after the
just
room's
reach
cleared
out.
we can get more questions there, but thank you so much.
Thank you.